Hi, welcome back. In this video we're going to continue our discussion on Coulomb's law. So previously we introduced the idea of the electric force using Coulomb's law and the electric field. And the idea with the electric field is that if I have a charge or some charge arrangement, there could be many charges, but I have some sort of field in here that we can't see, of course, but we can imagine. And that field creates a force. So if this thing is fixed, it's creating an electric field around it so that when I bring in like a test charge, here's my test charge, something is going to happen to that test charge. And if it's positive, we assume it's positive, it's going to go this way out radially. And the force it experiences is given by Coulomb's law. Right? Just in the way that, let's say we have the Earth, right? And the Earth is exhibiting, or not exhibiting, but is giving off some sort of gravitational field. And then when we put an apple, above the surface of the Earth, then, the apple is the test charge in this case, then the apple gets drawn to the Earth, right? So something happens to that apple. But we don't need the apple to imagine Earth's gravity. We know that it's there, and that's the idea behind the electric field as well. We don't need the test charge to know that there's an electric field around here, and we need to have an intuition about how it behaves. All right, but that's what we did in the previous video. This video is on continuous distributions, not point charges. So with continuous distributions, we need to use integration along with Coulomb's law. And we're going to work out an example. Most of this video is going to be an example, and it's not optional like some of the examples that I do. This example is critical to your understanding of the course. So the way we handle charge distribution, okay, is with we're going to start with a linear charge density. So we're going to use rho L. And we're going to call this a linear charge density. All right, and we're not going to confuse rho L with rho of cylindrical coordinates. Those are two different things. Rho L here is a linear charge density, and it has units of coulombs per meter. So in this video, what we're going to talk about are objects. They're three-dimensional objects, of course, but one dimension is much, much larger, longer than the other two dimensions. And in that case, we can approximate the object as just kind of a line. So we talk about how the charge is distributed along that line as rho L, which is coulombs charge per meter along the line. So if this line is uniformly distributed, which it usually is the case, if it's uniformly distributed, then rho L is a constant. The charge is equally distributed along the line. So let me give you an example. Here's our rod, or our wire, something that's we can approximate as one-dimensional, and maybe put the origin there, and this is maybe positive x. And I'll represent the charges by these plus signs. So something that is uniformly charged, or something that has uniform charge distribution, the plus signs would be equally spaced. The charges are equally spaced, so that if I take a slice of this thing, a length, maybe here's my length, we'll call that length delta x, and we will say we measure the charge on that slice as q1, then it's rho L, the charge density, times the length. So why is that? Well, remember the charge density is coulombs per meter, and so we slice this thing with something in meters, so we get the charge then. And the idea behind uniform charge density is, or uniformly distributed, is that if I take a slice then of equal length over here or somewhere else on this thing, so here's delta x, the same length, and we measure the charge on this thing, call that delta Q2, it's going to be identical. So that Q1 equals Q2. It doesn't matter where you take that equally sized slice, because the thing is uniformly distributed, you get the same charge, right? So let's compare that to something like this. Here's our rod again. Here's the x direction. Here's the origin, and maybe the charge density increases linearly. So maybe we have something like this. Again, those plus signs represent the charge. So if we repeat this, we take our slice here, here's delta x. This would be the charge density times delta x, right? And we take the same slice over here. The charge on that thing, we'll call that delta Q2. It's going to be the case where delta Q2, the charge on that slice is larger than the charge on the first slice. And so this would be non-uniform distribution. In this case, we would specify how the charge is distributed mathematically. In this case, we would have a constant or a uniform charge distribution. Now, we're going to consider an example, and this is just one example, the rest of the video. And the process here is just as important as the result. You've got to understand this process. And if you can understand the process, that means that you can find the result for different distributions, different examples than the one that I'm going to give you. So in this example, if you had a good physics teacher, if you had a good calculus teacher, then what we're going to do in this example should not come as a surprise to you. But if you're a little weak in physics, if you're a little weak in calculus, then this might be a little tricky at first. So what we're going to do is we're going to suppose that we have a line of charge like this thing. We're going to call that line, that length L, and it has a uniform charge distribution of rho L. We're going to find the electric field anywhere on a line perpendicular to the line of charge and passing through its midpoint. So we're going to find the electric field anywhere on this line that I'm drawing right now. All right, so let me simplify the drawing. So here's my, we'll say this is my rod of length L, right? And we're going to find the electric field anywhere on that line that's perpendicular to its midpoint. So here's the process. First, we're going to choose a coordinate system by identifying symmetry in the problem. So here come those coordinate system ideas. Since the rod looks the same, exactly the same as we rotate around it, right? We identify some radial symmetry. So it doesn't matter as we rotate around the rod, it's the same rod, it looks the same. However, it's not true when we go this way, because if we move up the axis of the rod, then we get closer to one of the ends, right? So we do not have symmetry this way, but we do have radial symmetry. What we've just described here is cylindrical system. We have radial symmetry in a plane, but not in the z-axis. All right, so we know we're going to use and we're going to work in the cylindrical coordinate system. Next, what we want to do is orient the axes, or the rod, to exploit this symmetry. So we're going to have the line of charge along the z-axis, and we're going to put the origin, it makes sense to put the origin at the midpoint. So here we go now. Here's my, let me draw my z-axis. I guess I should give myself some space. I'm going to erase this picture. All right, so here's the z-axis. Right. Here's the x-axis coming out at you. Here's the y-axis. I'm going to put the rod, and here's negative z-axis. I'm going to put the rod right here. Along the z-axis, so that its midpoint is at the origin. Okay, so that makes this height here L over 2, because the rod has a length of L, and that makes this height here, or this Z coordinate, minus L over 2. Next, and again, here's where your math and your physics comes into play, if you had a good physics or calculus teacher. Take an incremental change in the line of charge located, and we're going to call this at Z, maybe Z prime. So let's just consider an incremental change in the rod. And we're going to say, because it's so fine, the start and the end location are basically at the same location. We're going to say that location, it's on the rod, so it's got 0x, 0y coordinate, and we're going to say that that is at Z prime. This is the notation that we'll often use in our course. Z prime represents the location of an infinitesimally small or thin point that we're considering. And we're going to say its thickness is dz prime. So that thing has a thickness of dz prime, like that. Now we ask ourselves, what is the charge on that infinitesimally thin slice? Well, that would be dq then, representing an infinitesimally small charge, is the charge density times the thickness. Just like we did over here, right? We took the charge density and we multiplied by the thickness, and that gave us the charge. Same thing here. Now we're going to consider the electric field at some point on the midpoint. So the problem was to find the electric field anywhere on the y-axis, on the midpoint of the rod, passing through the midpoint, that is. So let us just say this point here. It's not on the y-axis, excuse me. I guess anything that passes through the midpoint that's perpendicular to the rod, so it could come out here. It's on the xy plane though. So we'll consider this point here, and we'll be general, and we'll say that in cylindrical coordinates, that thing is rho distance away from the z-axis at an angle phi, but it has a height 0. And it has to have a height 0 because that corresponds to passing through the midpoint of the rod. And I'm going to draw a vector here. From our infinitesimally thin slice to our field point. So we'll call that the field point. And so that infinitesimally thin slice creates an electric field at that field point. We're going to call that dE, for like a differential electric field. The distance from dz prime to any field point located at rho phi 0, or the distance vector, I should say. So here's the distance vector, r prime, or our arrow there, is rho a rho minus z prime az. Why is that? In getting from the infinitesimally thin slice to our field point, right? We have to go in the rho direction by rho. So that in this figure that I've drawn, that's kind of to the right. So that's that. And then we have to go down, negative, by z prime to get to the midpoint, right? Because this slice is at z prime, so we have to go down by z prime, so negative, in the z direction. So that's that vector, r. All right, we are considering what's the electric field at this field point due to this fine slice of rod there. And so the length of this thing, I'm going to draw that down here, the length of that distance vector from Pythagoras is the square root of rho squared plus negative z prime squared. And of course that we can drop the negative. That's rho squared plus z prime squared. Alright, now we're ready to write what that differential electric field is. So this is just the electric field due to this little slice. And we're considering just a little slice because that's the only thing we know what to do right now. We only know about point charges. So if it's a fine thin slice, then it's like a point charge. So we know that the electric field then is K times the charge, and the charge is dq, we're saying, a small charge, r squared times a unit vector in that r direction. And a unit vector in that r direction is r over r. So this becomes r cubed down there. So in cylindrical coordinates then, this is k dq. We've already said that r is up here, so this is rho a rho minus z prime a z over, and then the distance, then we've got the distance here, so this is like rho squared plus z prime squared to the 1/2, and so when you cube it, you've got it to the 3/2 power. So I'm going to write it like this. This comes up quite a bit, so we'll just get used to seeing this 3/2. It's kind of strange in other subjects, but in electromagnetics the 3/2 power comes up quite a bit. Again, so this is the electric field now at the field point rho phi 0, just due to this little fine slice of rod. So all of these little fine slices, or these incremental changes, z prime, go from negative L over 2, right? We have a slice here, and a slice here, and a slice here, and a slice here, all the way up to positive L over 2. So if our differential electric field, dE, is equal to this thing, then our total electric field now is the integral. So we need to sum. You know, the integral is like a continuous sum of these things, which hopefully you learned in first semester calculus from your awesome calculus teacher. Okay, so we have this. And then remember that, so here's the differential electric field. So I'm integrating all of the little electric fields along the continuous distribution. dq is rho L dz prime. So, and rho L, we're saying, is a constant. It's uniformly distributed, right? Rho L is a constant. And so we can take rho L out, and we can take the k out. And so we're left with k rho L. Then we're going to integrate z prime. The z primes are the location of these slices. They go from minus L over 2 to positive L over 2. And we have rho a rho minus z prime az rho squared plus z prime squared, all to the 3/2, and then we have the dz prime. Okay, now I'm going to give myself some space and erase this to the left. Now from the figure, observe that the z component of E will cancel. For this little guy, this little slice of rod, we have the same due to symmetry down here, which is going to push, we'll create an electric field like this. and the z components are equal and opposite. So because of symmetry, because we put this thing at the origin, this will always be the case along the z direction. And mathematically, so this is the symmetry argument, right? But mathematically, you see in z prime, this is an odd function. We have an odd function in the numerator divided by an even function in the denominator. That makes an odd function in z prime. So that is all to say, we do not have to consider the AZ direction. The AZ direction of the electric field will be 0. This is critical that you're able to see this, and you'll be able to see this with enough practice. But this is why we're using cylindrical coordinates, and this is why we set up the problem the way we did. So now we're leveraging that symmetry. So now the electric field becomes this thing, K rho L, the integral from negative L over 2, rho, A rho, over rho squared plus z prime squared to the 3/2 dz prime. So you see I've dropped the AZ direction again because I know that it integrates to 0. Now this becomes a math problem. We have to solve this integral, and you can use integral tables or you can use trig substitution. This integral comes up quite a bit, and so I'm going to show you the trig substitution, and later on in the course we will just kind of use this result. So I'll show you the trig substitution at least once. Here we go. So I'm going to let z prime equal rho cotangent of alpha, and then the derivative of that is rho times minus cosecant squared of alpha d alpha. Trigonometric substitution here, ladies and gentlemen. So this becomes K rho L, and I'm gonna leave off the bounds actually because I'm making a substitution, and then this becomes negative rho squared cosecant squared alpha over rho squared plus rho squared cotangent squared alpha to the 3/2 d alpha in the rho direction. I forgot the rho direction up here. All right, so this is just making a direct substitution everywhere there's a rho, or excuse me, everywhere there's a z, I put in this thing, and everywhere there's a dz, I put in this thing. All right, so I can simplify this a little bit, bring the negative out. I'm leaving off the bounds on purpose. Cosecant squared alpha. This gives me a rho squared cosecant squared alpha, all that to the 3/2 d alpha in the rho direction. So this is why I made the substitution actually, because the denominator using 1 plus cotangent squared equals cosecant squared, the denominator simplifies nicely. And then here's where the magic really happens. So now I can write this as negative K rho L, rho squared cosecant squared alpha. If I bring in that 3/2 power, I've got rho to the 3rd cosecant to the 3rd alpha d alpha a rho. And now, yep, you see it now, minus K rho L over, I'll bring out one of the rhos, the other two cancel, and I'm left, and the cosecants cancel, and I'm left with 1 over cosecant alpha d alpha a rho. Nice, right? This is why we're doing the trig substitution, and so I've got those constants out in front. 1 over cosecant of alpha is sine of alpha d alpha. We know this one now. So the sine integrates to negative cosine, so the negatives cancel. And I get this. Now we've done the integration, so we need to get our z's back. And up here we said that cotangent of alpha was z prime over rho. So I'm going to draw a right triangle. Call this angle alpha. Cotangent is adjacent over opposite. So if cotangent of alpha is z prime over rho, then this must be z prime and this must be rho. And that makes this hypotenuse z prime squared plus rho squared square root. So what is the cosine of alpha? Cosine is adjacent over hypotenuse. So that would be z prime over this thing here. So now our electric field becomes k rho L over rho z prime like this. Right? That's the cosine of alpha. Cosine of alpha right here, adjacent over hypotenuse. And now that I have the z primes back, the z primes go from L over 2, minus L over 2 to L over 2. So I'm bringing those bounds back. Okay, so I plug in the bounds and do the subtraction. And I get this as a result. So let me erase a little bit of this. All right, what we just did then is we found the electric field due to a long, thin rod. Here it is, of length L and charge distribution rho L. So it only has an electric field in the rho direction. So that's that circular, it radiates out like this. The electric field radiates out. That's why we're using cylindrical coordinates actually. Now, sometimes what we'll do is we'll say that the rod is infinitely long. So that means L goes to infinity. And of course rods aren't infinitely long, but what that means is our field point that we're testing, maybe is very close to the rod compared to the length of the rod. So when we say something like an infinitely long rod, we mean the dimension of the rod, the length of the rod, is longer than other relevant dimensions. So maybe we're testing field points around here. Right? We want to know the electric field around here. So around there, the rod appears approximately infinitely long. All right, so in that case, it's useful to consider this limit as L goes to infinity. So what is this thing? This is the electric field. What does that do as L goes to infinity? Well, when I add rho squared to something that's infinity, that doesn't have any effect. So the L squared over 4 can come out of the square root and become L over 4, or L over 2, excuse me, and the L's cancel, and so then I have that 2 that will come up to the numerator. And so for an infinitely long rod, I get K rho L over rho. And that's the result. And this is, again, infinitely long. And this was the result for finite length. Now, when you consider the rod to be infinite in length, then this thing will apply anywhere, not just on this axis, right? We started this problem, we said that it has to, we're finding the electric field on a line that's perpendicular and passes through the midpoint. But now that we've considered the rod to be infinitely long, as long as we stay away from the edges of the rod, then this infinitely long approximation applies anywhere, not just on that original line or that original plane. So that's it. And I'll oftentimes get the question now from students when we're in class, do I need to know this process? So that, do I really need to know this? Yeah, you do. Okay, you need to know this. This is an important process, what we did here, even the mathematical integration. But I'll just summarize it here for you again. We chose the coordinate system first, right? We identified the symmetry and we chose the coordinate system. That's important. Yes, you need to know how to do that. Then you need to know how to orient the problem to take advantage of the symmetry. In this case, we put the rod in the center, or we put the center of the rod in the origin, at the origin. So then we can leverage these symmetries. Then we sliced the rod in infinitely thin slices so we can consider it to be a point and apply Coulomb's law. And then we integrated over the rod, right? And we did the integration. Do you need to do all of that? Yes, you need to know how to do all of that. And we'll look at other examples too, of course. All right, so I'll see you then.